Hi everyone, welcome to the Calculus Integral Calculus course. My name is Yuri Burda. Over there I've written some information about how to contact me. Email yburda, yburda, @math.tbc.ca. An important website, the website for our section is over there, sites.google.com/site/yburda/math-105. I'll post different kinds of information over there, like lecture notes. So if I write down some lecture notes, lecture videos, I'll try to record the video. The camera over there, we'll see how it works. Corrections, so whatever I so all the information relevant to our section will go on this website. I will hold office hours for this course. You see it's summer course, it's very intense, so we have 4 lectures every week, and 4 meetings every week, and for office hours, Monday, Wednesday, Thursday, and Friday. It's an Earth Science building. So about the course, we'll be using this book. It's Calculus Early Transcendentals by Briggs and Cochran. We'll use edition, it's called Second Custom Edition for UBC. It's basically quite similar to what's called in other places International Edition. We have this one comes in 3 volumes in UBC Web bookstore. We'll use volume 2 and volume 3. The mark for the course, the grade for the course will be decided by 5 grades. Most important is the final, 50%. We'll have 2 midterms on week 3 and week 5. Each midterm is 17% of the grade. We'll have web work, 10%, and we'll have in-class quizzes, 6%. So let me say a couple of words about web work and quizzes. The web work, we are setting it up. I hope that by Friday we'll have the first homework ready for you. In general, we'll try to post the web work on Friday and close it by Monday of the next week. So we have 2 weekends to work on the web work. For quizzes, I hope we'll use clickers in class. So I hope we'll manage to have question on the board. Each one of you will have a clicker and you'll choose one of the 5 answers. If the system works, so to be honest, I've never used clickers in the class, so if the system works, that's how it will be. The quizzes in general will be in the beginning of the lectures, so try not to be late. And I'll try to make sure that it's pretty easy to get this 5-6 points for the quizzes. The marking scheme for the quizzes will be 1 point for participation, 1 point for correct answer, so each question will be graded out of 2 points. You get 1 point for just trying the question and 1 point for getting the right answer, and 70% counts. So if for some reason you cannot attend, say, one of the meetings every week, well, we still have the chance of getting the 6 points. Okay, so we'll try to set up the system the first time tomorrow. I'll try my best to set up the system tomorrow. You should, before the next class, try to register your clickers. So you should go to the Connect website for our course and click on the link, something like clicker registration, and on your clicker you'll find some ID number for the clicker. You should register to the clicker for our course. Okay, so this is the kind of administrative information about the course. So maybe you have any questions? Yeah? Yes. So the quizzes, well, if the system works, which I'm not sure that it will, if the system works, we'll use clickers. Yeah?
In regards to the technical, I was just at the bookstore, and the only one they had from Mac is that for volume 2.
Okay.
It said that there's no volume 2 required.
No volume 3? Okay, I'll check this. I don't know what that is. Okay, I'll check. Other questions? Oh, so I switched to 3 and 2. Maybe I'll check. So for now I have, well, indeed on the volume 2, but yeah, but I don't know.
And that's what they've got at the bookstore.
Yes, and then this. Okay, sorry. It is a third Other questions? Okay, so if there are no questions about the administrative part, let me make a short advertisement about the course in general. It is a continuation of the previous course, Math 104, which was about differential calculus. It was all about rate of change of a function of one variable, and our course is called integral calculus. Well, it's a little bit misleading. It's not that we are only going to talk about integrals, although a large part of the course is devoted to integrals. We'll have three main topics. One is functions of several variables. So unlike in the previous course where all we had is function of basically just one variable and we will try to differentiate it, maximize it, whatever. In this course we'll have functions that depend on several variables. And so in fact in life things do depend on quite a lot of different factors. So for example, a volume of a box, well, it's a function of three quantities: width, length, and height. So basically, every function is naturally a function of more than one variable, and we'll develop some theories on how to work with such functions. Another topic will be integration. So, in the previous course, we studied the process of differentiation, which was given a quantity which changes over time. The question was how fast it will change. In integration, we'll be talking about, well, kind of converse of this operation. You'll be given how the quantity changes, and the question will be how these small changes accumulate over time to produce one large change in the quantity. So that's the process of integration. And finally, we'll talk about series or approximation. And when we'll talk about this, we'll talk about the question, well, given a function which is complicated, something which you may not be able to write down, how to approximate it by much simpler functions. Some trigonometric functions, some polynomial functions. So that's probably the last week of the class. Well, we'll see some small applications of these topics, maybe some applications of probability in the chapter about integration, the application to maximization, functions, such things. So that's in short what the course is about. So once again, maybe any questions about the outline of the course. Maybe just a small remark. The course is, well, the summer course, it's only 6 weeks long, and it is extremely important to follow the course. I mean, once you get lost, I don't know, in the middle of week 2, and you wait for just 1 week, well, you basically got lost about 1/6 of the material, which is quite hard to kind of catch on. So every time you have any question, anything is not clear, so if it's a small question, stop me and ask me. If it's a large question, like I don't understand the whole lecture number 2, well, come to the office hours and ask. Don't wait with this. And of course, work on the assigned problems. We'll have the web problems, we have suggested problems from the book. You don't have to submit them, but do try to solve them. It's quite important. Okay, so let's start talking about math, actual mathematics. Our first topic is space, three-dimensional space. Somehow when we talk about functions of several variables, well, just drawing pictures on the plane is not enough. Sometimes to understand how functions of several variables work, we have to draw some pictures in the space, in three-dimensional space. And so how do we talk about the space? So in the plane, we usually talked about points as having 2 coordinates, x coordinate, y coordinate. Once you know x coordinate and y coordinate, you can locate a point. Well, three-dimensional space is quite similar, but now it has 3 coordinates. I'm drawing such a picture with x-axis, y-axis, z-axis. You should think about it as actual three-dimensional picture. So here I'm standing in the corner. This way is z-axis, this way is, let's say, x-axis, this way is y-axis. So here are the axes. That's the picture that I try to draw here. And every time you have a point, once again, you can assign coordinates to this point. If I pick a point somewhere in the space, well, you can try to find out what the coordinates are. You can project this point onto the x-axis, onto the z-axis, onto the y-axis, and find out what are these distances. This distance, and that distance. Well, let's say that this particular point had this distance equal to 1, this looks maybe like 2, and this looks like 4. Then we say that this point has coordinates. It has coordinates along the x-axis. The coordinate is 4. Along the y-axis, the coordinate is 1. Along the z-axis, the coordinate is 2. And vice versa. If you know just 3 numbers, which are the coordinates of a point, you can find out where in the space this point is located. If I tell you, well, find the point with coordinates 1, 2, 3, well, let's say 1, 2, 1, and the coordinates are in meters, well, this is my coordinate. I tell you coordinates 1 to 1, well, 1 right here, 2, I make 2 steps to here, and 1, and go 1 step up. So here's the point with coordinates 1 to 1. Go. So basically talking about points in the space is the same as giving 3 numbers. there isn't much I can talk about. I can tell about points. Let's talk about a different kind of thing called vector. Another useful operation, besides just locating a point with 3 coordinates, is, well, how to go from one point to another point. And that's the notion of vector. Vector is about a direction, an arrow, a displacement, how to go from one place to another place. So typically we draw a vector as an arrow. Once again, we have a system of coordinates, and we might wonder how to go from one point to another point. The arrow which points from one point to another, well, is called a vector, and once again it's given by 3 coordinates. How much did you move along the x direction, how much did you move along the y direction, and how much did you move along the z direction. So maybe this vector is, I want to move 3 units in x direction, 1 unit in y direction, so kind of out of the board, and 2 units up. So here's a vector. What's special about vectors, they are the abstraction of, well, the notion of displacement. You don't attach a vector to a particular point, you don't really remember what the origin of the vector is. You just tell, well, a vector with coordinates 3, 1, 2 is kind of prescription. Go 3 steps along the x direction, 1 step along the y direction, and 2 steps along the z direction. You don't tell where to start, you don't tell where to finish, just how much to move. Next question is, what are these vectors good for? What can we do with them? So there are several operations which are very natural to do on vectors. One of them is addition. Suppose that you want to move first like this, 1 step in direction x, 2 steps in direction y, 3 steps in direction z, and then you want to move like this. 5 steps in direction x, 2 steps in direction y, 1 step in direction z. Well, what is it? It's exactly the same as moving 6 steps along direction x, 4 steps along direction y, and 4 steps along direction z. So when you want to add 2 vectors, basically add 2 arrows. Something like this. Imagine 2 arrows, and the question is, you want to move from the starting point first like this, and then from here follow the second vector. Well, the sum of the 2 vectors is something like this, and to find out what is the sum, you just add the coordinates. First coordinate to third coordinate, second coordinate to second coordinate, and so on. So that's very simple operation. Another natural operation is multiplying a vector by number. So if you have a vector 1, 2, 3, and you want, let's say, move in the same direction, but 3 times as far, how would you do this? So you take this vector and multiply it by 3. Instead of moving 1 unit in the x direction, you will now move 3 units. Instead of moving 2 units in the y direction, you now move 6 units and 9 units in the z direction. So if you have a vector, you can multiply it by a number, and that's just moving in the same direction, but well, in this case 3 times farther. So this is 3, this will be 3. Another useful thing, well, suppose you have two points in the space, and you want to find out how to move from one point to another one, to the second one. How do you do this? So, let's say the vector pointing from position 3 to 7, 6, 5. So now I give you 2 points in the space, and the question is, what vector do you have to add to the first point to get the second point? So in what direction you should move from this point to get to that point? Well, that's very easy. Indeed, how much should I move in x direction so that my x coordinate will change from 1 to 7? 6, of course. So what I did is just subtract this 1 and this 7. So the answer is like this. I take my m point and subtract the first point. And the answer is, well, I should have moved 6 units in the x direction, 4 units in the y direction, and 2 units in the z direction. So this vector is a vector which goes from here to there. In other words, if you start here, you add this displacement, you end up here. So that's the picture is somewhat like this. This is the origin. This is, let's say, 1, 2, 3. This is 7, 6, 5. So to go from here to there, we have to move along the vector 6, 4, 2. Okay, so maybe any questions so far? For now it was really simple, just introduction of the concept of what vector is. It is an arrow, it is displacement. Okay, next let's talk about the dot product. A little bit more tricky concept. Suppose you have 2 vectors. One vector is v, with coordinates v1, v2, v3. Another vector is w, coordinates w1, w2, w3. We introduce a funny operation called a dot product. We kind of multiply 2 vectors, but the answer is not a vector. It will be a number. And this number is going to be the following. v1 times w1 plus v2 times w2 plus v3 times w3. So what happens is we multiply the coordinates, first coordinate by first coordinate, second coordinate by second coordinate, third coordinate by third coordinate, and we add up the results. Let's say, here I write an example. If I have vectors 1, 2, 2, and I want to find the dot product of vector 1 minus 2, 2, the result is 1 times 1 plus 2 times 2 plus 2 times 2, and the answer is 1. So dot product of 2 vectors is a number. It looks like a funny operation. We took two vectors, produced a number. Initial question is, why do we bother with this operation? Well, here's the vector. No, it's not obvious, but it is correct. I'll write it as a fact. Will not really explain why it is true. It's It should be taught in linear algebra courses. It turns out this number, this dot product, contains lots of information about the geometry of the situation. If you have two vectors, you can compute the dot product, well, in two different ways. One is this kind of definition, another one is this way. You compute the length of the vector v, this is length. So when I put a vector in an absolute value, I mean just find out what the length of this vector is. Multiply by the length of vector w, and then multiply by cosine of the angle between v and w. So this dot product actually knows quite a bit about the mutual location of these vectors. Yes.
What's that symbol after the cos? What was W?
Cosine of angle between v and w.
Okay.
So this will be angle between v and w. So here are the vectors, v and w. There is an angle between them. So one way to find out what is the dot product is as follows. Compute, just measure, take a ruler and see what is the length of the vector v. Take a ruler, find out what's the length of w. Measure this angle, and compute this expression. Length of v, length of w, times cosine of the angle.
Is the angle expressed in radians or degrees?
It doesn't matter. I mean, just measure the angle and compute the cosine.
So, but we don't have to calculate this,
Once again, it doesn't matter. I mean, is the length in centimeters or in meters? It doesn't matter. Is the angle in radians? I mean, the angle is an angle. How you measure it is, how you write down the result of the measurement in radians and degrees or in centigrade, well, doesn't matter. It's just a quantity. You can take the cosine, get a number between -1 and 1, and the cosine. So once again, I don't explain why this formula is correct. It's also not that obvious. But it is correct. And it allows you to learn something about mutual position of two vectors. For example, it gives you a way how to compute the length of a vector. If you are given the vector in, well, these three coordinates, what is the length of the vector? So for instance, if you take the vector and find the dot product of the vector with itself, which we know how to compute. If you have three coordinates, we'll just use this formula. According to this formula, it's the length of v times the length of v times cosine of angle between v and v, which is 0. So it is the square of the length. So this formula tells you how to compute the length of a vector. It's the square root of the dot product of the vector with itself. So here I've written what is the dot product of v with itself. It's the sum of squares of coordinates of v. So maybe I'll put in a box some important formulas. Basically, you should remember these formulas. Now let's do something more fun. Let's find out, given two vectors, what is the angle between them. So it's all an exercise. Find angle between v and w So the question is, you are given two vectors. You can try to imagine how they look like. X, Y, Z. So V is one step in X direction, two steps in Y direction, two steps in Z direction. So probably something like this. W, one step in X direction, negative two steps in Y direction, and two steps in Z direction, so something like this. The question is, what is this angle between V and W? Okay, so let's answer the question. Here's the formula which involves the angle. We can rewrite it as cosine of the angle between V and W being the dot product V and W divided by length of V and divided by length of W. Exactly the same formula. Now I can compute those. The dot product of V and W, so it's 1 times 1 plus 2 times negative 2 plus 2 times 2. Length of V, square root of some squares of coordinates. Length of W, or similar expression, square root of some squares of coordinates. And now we get a number. 1 in numerator, 9 in denominator. So here it is. The cosine of this angle is 1 over 9. Well, what is the angle? Well, we have a name for it. R cosine of 1 over 9. If you take your calculator, well, now it makes sense to ask in what units do you want to measure it. Well, it doesn't really matter, but let's say degrees. 83.6 degrees. And that's only approximately. Okay, so what this dot product allows you to do is find out, say, what is the angle between two vectors. Quite powerful if you think about it. Look at the picture. Yes, we do see that these vectors kind of point in different directions. One points this way, another one points that way. What is exactly the angle between them? Well, I have no idea. It looks, well, kind of close to 90 degrees, maybe a little bit more, maybe a little bit less. My picture is not that good. This formula allows you to find out precisely what the angle is. Turns out to be 83.6 degrees, so a little bit less than 90. Okay, so maybe any questions about the dot product? Dot product lengths, angle between vectors.
So could
Yeah.
you explain how you put the how you get that V times W over the length of V over times?
It's exactly the same formula, just I rearranged. I
Oh.
take the term cosine, I leave it on this side, and I take the length of V, length of W, and I divide it.
Okay, that's it.
Hmm? Yeah. Okay. Yeah.
Sorry, but how did you get that equation there?
Over here.
How did you form it?
So I try to find out what is the dot product of vector V with itself. According to this formula, it's just, well, the square of length of V. And then I write that length of V is just square root of the dot product of V with itself. Okay, so now we know a little bit about kind of how to find an angle between two vectors. Let's talk about two very special mutual positions of two vectors. So let's talk about parallel vectors. And then we'll talk about perpendicular vectors. So it makes sense to ask the question, do these arrows, and no, this arrow and that arrow, do they point in the same direction? It's a meaningful question. They might not be exactly of the same length. You might take an arrow and kind of stretch it. So the question is, how do we know that two arrows are just basically the same direction but different lengths? So two vectors are parallel if one is a multiple of another. So here are two vectors which I try to draw parallel. One vector, if you stretch it by a factor of 2, you'll get this vector. Well, in numbers, if you are given two vectors as their coordinates, so here's an example. Let's say 2, 4, 6 and 3, 6, 9. Are these two vectors parallel or not? Well, the question is, can we stretch one of these vectors by a factor and get the other vector? Well, yes. You can take this vector, and you see if you stretch it by a factor of 3/2, you'll get this vector. So these are parallel. This vector is 3/2 times 2, 4, 6. In other words, the quotients of the x coordinates, y coordinates, and z coordinates are all the same, 3/2. If you take 3 divided by 2, or 6 divided by 4, or 9 divided by 6, you get the same number, 3/2. So if you take this vector and multiply it by 3/2, you'll get this vector. On the other hand, something like 0, 1, 0, and 1, 0, 0 are not parallel. So if you just look at the numbers, it's quite obvious that if you take this vector, multiply it by any number, you'll get something like 0, number 0. Never something like 1, 0, 0. Geometrically, well, this vector points in the y direction, this vector points in the x direction. They obviously are not parallel. And maybe one small subtlety. Multiple, these 3/2 could be positive or negative. We say that two vectors which point which define the same line but point in different directions along this line are still called parallel. So we mark. Two vectors, and you can multiply one of the vectors by a negative multiple and get the other vector, they are still called parallel. So what we care about is just the direction of this vector, but really without the arrow, just the line which this vector defines.
So what you mean to say is basically if you took one set
I'm just saying that when we are talking about two parallel directions, well, at least in this context, we don't mean the direction as an arrow, just a direction kind of along a line. So the direction along this line can be chosen either from here to there or from here to there. We still say that the two directions are parallel to each other. Okay. Another interesting mutual position of two vectors is when they are perpendicular. Well, it's just the angle between two arrows being 90 degrees. It's happens quite often in, say, engineering. The angle between this vector and that vector is 90 degrees. For some reason, we love angles of 90 degrees. And the good news is it's really easy to detect whether two vectors are perpendicular to each other or not. V is perpendicular to W exactly when V dot W is equal to 0. So why is it so? The angle between two vectors being 0 means that the cosine, the angle being 90 degrees means that cosine of 90 degrees is 0. So the dot product, which is length of V times length of W times cosine of 90 degrees, must be equal to 0. And vice versa. If the cosine is 0 of some angle, then this angle is 90 degrees. So for instance, it's really easy to detect that this vector and this vector are perpendicular. All we have to do to show this is compute the dot product. 1 times 1 plus 2 times 1 plus negative 3 times 1 is equal to 0. The dot product is 0. The vectors are perpendicular. So maybe any questions about the dot product and these two special mutual positions of vectors? Parallel vectors, perpendicular vectors. Yeah.
Could you please explain what you meant with that remark up there? I don't understand what you mean.
Which one? Here?
No, the parallel, the parallel.
Parallel. I'm just saying that there are several possible basically conventions. When you're talking about parallel directions, do you mean that, say, so here are two directions. One is from here to there, another one is from here to there. The question is, do you regard them as parallel or not? And that's not a matter of kind of substance, it's a question of definition. So my definition is, yes, we do regard those as parallel. We only talk about the line from here to there being the same as the line from here to there. And in this sense, these two directions are parallel.
Like the arrow direction doesn't matter, but just it's all like a shape.
Yes.
How they match matters.
Exactly. So if you put kind of these two vectors tail to tail, they form a straight line.
Yeah.
Yeah.
About the parallel vectors, in opposite direction, it would still be parallel if the second one was -1, 2, and 3, right?
No.
One of them
No.
was -2.
So if you try these two vectors, 1, 2, and 3, and 1, -2, -3, these two vectors are not parallel. Well, in numbers, you cannot multiply this vector by number to get this vector. If you multiply it by 1, you'll get the number, the vector 1, 2, 3. If you multiply by -1, you get -1, -2, -3. There is no way to multiply this vector by a number, a single number, and get this vector. Other questions? Okay, so let me just start with an announcement of what we're going to do next time. And then we'll finish for today. So next time we'll start with equation of the plane. So we discussed points, we discussed kind of arrows in the space. Now let's talk about planes in the space. So a plane is something like, well, this. The definition of a plane is, well, defining property of a plane is if you have 2 points on the plane, the whole line between these 2 points is also contained in this plane. And you can play with this definition and see that planes are exactly the shapes in the space with the property that together with 2 points, they contain the whole line between the 2 points. Okay, and next time we'll see how to describe points, all the points in the game plane.